And I put the grades up on Moodle. So typically with those quizzes, those grades are going to go up pretty fast. I didn't send out an email because, y'all have a lot of quizzes, but they go up pretty fast. So just check back at Moodle and you'll find your grade there. Just a note about the quiz grades weren't really that great, honestly. There wasn't even, not even one person got a perfect score. The highest score was they missed one question. So I feel like these questions, like if you read the chapter, I feel like they're fairly straightforward. But I don't want to alarm you, but I sort of say that the quizzes aren't worth much, but they are worth 50 points. So like don't blow them off. Make sure that you're reading carefully, and that'll really help you with the exams. Okay. Now I will try to get as many quizzes as possible so that we can drop some, but you really need to do well on the quizzes too. I feel like I've sort of minimized them too much, but they are important and they are a big part of your grade. Okay? But don't be discouraged because we have lots of quizzes. Also, if you look on the website, we're doing this food drive thing, and I sent out an email about that. Did everybody get that email about the food drive? So the way that works is it's 10 points. It's corporate, so it's not just y'all. It's all of my classes. And for every 100 items that are brought in, you'll get 1 point added to one of your exams. It just sort of goes into the pot. So it could be 10 points to a quiz, 10 points to an exam, whatever. It's all the same. But if you go on the website, like if you're a person that likes to track things, you can go to this. This is cool. That's okay. Look, there's a bar graph here, and you can track how many things have been turned in. So this is by class. So this is my Physics 202 class with this big column right here, and nobody else has turned in anything. Isn't that neat? And so it's updated in real time. 24 items have been brought in. They brought in a case of water, or a student brought in a case of water. But you can also, I'm not saying that you have to donate cash, and if you donate, it doesn't really impact your grade other than the 10 points. Like if you donate, what? It's not insubstantial. It's a couple percentage points. I appreciate if you make any donations, but it's not going to impact your grade otherwise, other than some points. Does that understand what I mean? But so with that said, another student said that he was going to donate $200, and so if you'd rather donate cash, it's $1 per item. So if he donates $200, that'd be like 200 items. But that goes to all of you, okay? So, all right? Okay. I think that's kind of fun. All right. We left off last time with conservation of mechanical energy. Let me just ask you a couple questions to warm you up. Remember we worked the cheerleader problem? Hey, who went out and tried that? Like had your friends throw you up in the air and go through the basketball hoop? Nobody? Yeah. I tried to do it to my son, but then my wife stopped me. She's like, no, don't do it. So remember the cheerleader, she went up and then she came back down again. At which of these points, I'll call this A, we'll call this B, C, and D, which is at the halfway point. All right, at which of these points is the potential energy greatest? We called this U, didn't we? At which point is U the greatest? At which of these points is the gravitational potential energy, U, the greatest? You might say the potential energy is great regardless of where it is, but I mean like the numerical value. Where is the numerical value the largest? We're going to be in it for a while. All right, I'll stop at about 45. I think I have more than 36 here today, don't I? Just a few more seconds. Okay, very good. C. All right, where is the velocity greatest? Where is the velocity greatest? At which point? At A, B, C, or D? Where is the velocity greatest? Doesn't matter. I mean, we can say it's just on that side, the going up side. I'm asking about the speed actually here, so the speed, so not the sign of the velocity. All right, I'll stop at 45. 45. Where's the velocity greatest? No, seriously. Okay. All right, guys, listen. The velocity is greatest where the kinetic energy is greatest, right? Now, we've already said that up here, the potential energy is greatest at this point, right? So at what point is the kinetic energy the greatest? A, B, C, or D? A, right. The kinetic energy is greatest as A. Just as they throw her up, she has all kinetic energy and no potential energy. No, she's flying up in the air. Okay, let's try it again then. I'm sorry. I just won't count that previous question. I won't count the right answer. But nobody got it right anyway, so it doesn't really matter. All right, so let's try it again. Where is the velocity greatest? I'm not saying outright the answer is A, but that seemed to be what y'all were implying. All right, just 25. I'll stop at 25. Okay, very good. And where is the potential energy equal to the kinetic energy? At which of these points, A, B, C, or D, does the potential energy equal the kinetic energy? And that would also imply that the potential energy is at half its value, or that the kinetic energy is also at half its value. Right, so where is that? The potential equals the kinetic energy. All right, I'll stop at 42. 42. Hmm. Okay, let's try this again. So most of you put either C or D, and one of those is the right answer, either C or D. So let me tell you this, that where the potential energy is equal to the kinetic energy, that same location is where the potential energy at that location is equal to 1/2 of the total potential energy, or the maximum potential energy, because at some point it has a maximum potential energy, and at the point where this equals the kinetic energy, the potential energy is equal to half the maximum, or half of the total energy. You can think about it also as it's equal to 1/2 of the total energy. You could also think of it as being 1/2 of the maximum kinetic energy. All right, let's try it again. It is either C or D, so let's just give your hand at that. It's also the point where you have half the maximum potential energy, or half the maximum kinetic energy, or you could also say that is just half the total energy. Those are all the same statement. Think about, where do I have half of my maximum potential energy. Remember, potential energy is equal to mgh. Right, potential energy is equal to mgh. So what is the value for h where I have half the potential energy, half the maximum potential energy? Because about half of you are still wrong on this question. So at what location do I have half the maximum potential energy? Let me just remind you up here, do y'all remember the answer to this one? Where is the potential energy the greatest? Who remembers that? C was, right, C was the answer to that one. All right, that looks better. Okay, just a few more seconds. I'll stop at 132. I think there's still one of you holding out. Two of you. Okay, D is the right answer. At the halfway point, I have half of my potential energy, half of the energy is in potential energy because I'm at a position of h over 2, right? And so I get an h over 2 here, so I get a u over 2 here, half the total potential energy. At the point C is all potential energy, right? There is no kinetic energy. All right, good. We'll come back to this. We'll see some more. We'll see some more regarding this. You might think this is just sort of an exercise, but it's really quite important when we think about energy, about how energy is conserved within a system, right? That if you bring in energy into a system, then that energy is used in some way. And we'll see that with heat, and we'll see it with cooling and stuff like that, where this idea comes up again. And we're just sort of illustrating it with here a mechanical system. Okay. Let's now look at some different types of energy. And your book sort of has like a short paragraph on each of these. Types of energy. First of all, we have electrical energy. Have we talked about this? I think I listed them, right? But we didn't really. Okay. Electrical energy. Electrical energy is the energy of charges. It is primarily a potential energy. When we talk about electrical energy, it's a potential energy. Because if I have two charges, say two positive charges here, and I hold them in this location, they're going to tend to fly apart, right? So they have the potential for motion. If I have them here, they will tend to fly apart from one another. So these have the potential for motion. So they have potential energy. They have the potential for motion. Thus, they have potential energy. All right. The potential energy of these is greater when the charges are A, closer, or B, further apart, in which configuration, that is two charges that are very close, or two charges that are very far apart, two positive charges in this case. So I have, just like this situation that I have here, where is my potential energy greater? Where is the potential for motion greater? Is it when the charges are really close together or when they're really far apart? You might not necessarily know this, but I think that you might, so I just want to see. Oh, yeah. Where is the potential for motion greatest? When they're close together or when they're far apart? Yeah, they're two positive charges. Mm-hmm. Not touching, but they're either far apart or they're almost touching. They're close together. Where do they have the greater potential for motion? They could be touching. in this case. Remember, like charges repel one another, right? All right, good job. Just a few more seconds. I'll stop at 50. Guess if you don't know. We're going to cover electricity later in this semester, hopefully. A is the right answer. It turns out that as you move charged objects closer together, the charges between them increase. Or excuse me, not the charges, the forces between them increase. You've probably observed this. Magnets are similar. Magnets produce an electromagnetic charge that are due to moving charges. And when I bring magnets closer together, the force increases between magnets. A similar thing happens with charges. And when I have them closer together, I have bigger forces, and so that causes them to have more potential for motion because they'd go away faster than if they were further apart. All right, so electrical energy, and that idea will come back later when we talk about voltage and potential and stuff like that for electric charges. Internal energy. Internal energy is the potential and kinetic energy of molecules and atoms. All right, we would call this also, gosh, it feels like have we not done this? We just sort of introduced it, right? Okay. Uh, so this is, what do we call this, actually? Another word for this? Chemical energy. All right, yeah, chemical energy. This is also chemical energy, food energy, for example, chemical energy. But it's closely related to the electrical energy because, you know, if I have a molecule or an atom, say I have a hydrogen molecule. Hydrogen molecule are two hydrogen atoms connected by an electric bond, and they have a certain amount of energy because of the situation of these two charges. That if you were to liberate them in some way from this bond, they would emit a lot of energy. A lot of energy, right? Like the hydrogen bomb, for example. Or when we eat things, that energy that's held within those, that chemical energy is released into our body. All right, so internal energy, heat is another big one, and a big part of this chapter will be dealing with heat and the flow of heat. Let me go to the next page. Heat is the transfer of energy from a hot to a cold object. In particular, this is a type of energy that we'll call thermal energy. So whenever we talk about heat, we're talking about the transfer of energy. And the type of energy is called the thermal energy. Thermal energy from a hot to a cold object. Later today, probably, we'll get into thermal equilibrium and how heat transfers from one object to another. When heat is added, the temperature increases or changes phase. Or the material changes phase. Again, something we'll talk about later today, hopefully. I have a little clip. This is about this is a guy that wrote a book. He's actually like a physics professor, but he wrote a book about like the physics of basketball, and he's talking about here how a basketball, the actual ball, how it performs during the game, and what happens to the ball during the game. So as you're dribbling it and all that jazz, what happens to the ball? And so here, obviously, heat is going to come up, or maybe that's not so obvious. But this is an audio clip. It's really just for your own interest, so we'll just listen and. Don't worry about taking notes or anything on it. We'll just listen to it. All right. Again, a lot more about heat a little bit later. We have chemical energy, which we've already talked about a little bit. Did I tell you, by the way, this is sort of off topic, but did I tell you that both of my children, can I tell you this? Y'all care? No, you don't care. But I'm going to tell you, both of my kids, they won the book character day yesterday. Like my little girl, they dress up as a book character and then they give a little report about their favorite book character. And my little girl and my little boy, they both won like best in their class. You're gonna? Did I dress them? Not really. No, I mean they sort of designed their thing, and my wife she had to sew some stuff. But I did have an idea, which I'll tell you about in a second. It was my idea actually, which I'm very pleased with. But it was just a small part. But my little girl dressed up as Laura Ingalls. She's in kindergarten. Laura Ingalls Wilder, like Little House on the Prairie, and she had like a bonnet, a dress. She looked really cute. And then my boy, he's 9. He dressed up as Bilbo. You know Bilbo from The Hobbit? Or Lord of the Rings. You might have seen that or read it. But he had a vest and an old shirt that he had. He took some pants and just rolled them up. But this was my idea. Got some feet off the internet and printed them out on cardboard, and he like big Hobbit feet, and then just taped them to his shoes. It was cool. He had big old furry feet. All right. Not that you cared or asked, but I have some at home. I'll bring them next time. Okay, I'll try to remember to put them online. Okay, so chemical energy. This is a type of electrical energy, as we talked about. Due to molecules and atoms. Just depending upon how those molecules and atoms are configured, they can have a certain amount of energy. This energy is released in chemical reactions. Or in extreme circumstances, in nuclear reactions, you can release that energy as well. We have electromagnetic energy, which is akin to electric energy. And we'll have a whole chapter on this later, which is the energy due to light, so light radiation. Speaking of light as just a particular type of radiation, right? Light is radiation, but then there are other types of radiation that you can't see, like ultraviolet, infrared, gamma rays, X-rays, what have you. And then acoustic energy, which is sound. So there's a chapter on. And then finally, nuclear energy. I doubt that we'll get to, but there is a chapter in the very end. This is energy associated with a nucleus. All right? Okay. So those are just different types of energy. You just need to be familiar with them, sort of what they're associated with. Now, we've had the law of conservation of mechanical energy, but there's a greater law called the law of conservation of energy. And it's very similar, and it's probably going to look the same to you. It's really just sort of semantics. The law of conservation of energy. And this is opposed to, or similar to, what we said before, the law of conservation of mechanical energy. Remember with the mechanical energy, we said that the sum of the potential and the kinetic energy, that's always constant. But this would say that the sum of all of the energies is always constant. So the total amount of energy says in words, the total amount of energy in a closed system, I'll define what that means, is constant. Right, the total amount of energy in a closed system is constant. Or in equation form, you would say that En equals E out. Or not En equals out, I'm sorry. That E initial equals E final. That as I have a closed system, that the initial energy is always equal to the final energy. Right, so what are some examples of closed systems? So for example, am I a closed system? As I walk around out in the world, am I a closed system? And that would imply, let me define closed system before you answer. Means that there is no energy leaving or entering the system. So when I say this is regarding the law of conservation of energy, basically these two statements are basically the same. That if I'm not putting any energy into or out of the system, then the energy can't change. Right? Does that seem obvious to you? It's not an obvious statement though, because people didn't used to think that. Right? They thought that the energy would wane over time or whatever. So for okay, so me walking around, am I a closed system? No. What kind of energy am I losing? All types of energy, right? But mostly I'm losing what type of energy to my environment around me? What type of energy am I losing? Thermal mainly, right? I'm like a big old warm body. All of you are big old warm bodies and you're just constantly putting off heat. And so I am not a closed system because I'm losing thermal energy. So that's just an example that, so me or you walking around is not a closed system. I know that's not grammatically correct, I'm sorry. Yeah, Fazal? You are burning calories, but those calories are going to causing your body to function, and then that's converted into other types of energy. So like, for example, it causes your body to maintain a temperature, right? And then that temperature is conducted out to your environment around you, and so you're losing thermal energy. Or that those calories are converted into energy to power your muscles or whatever, and you're splitting wood or whatever. So that energy, that chemical energy, is converted into kinetic energy. All right? However, let's say that I'm just sitting in my office, you put me inside a box, and you shut the door. Is that a closed system? There's no air coming in or out. It's a sealed up box. Is that a closed system? Yeah? No? It is a closed system. That, I'm still losing thermal energy off of my body, but it's going into the box and it's heating up the box. So while that energy is transferring from one place to another, it is a closed system. So what this implies then is that any system that's open, that is, that's losing or gaining energy, can be made a closed system by doing what in your consideration of it? Put it in a box, isolating it, or making your view of the system larger, right? So the end result of that is that the universe is a closed system. From a physical perspective, that the universe is a closed system. Right? If we assume that there's no energy coming into or out of the universe, then it is, by definition, a closed system. Right? So you can enlarge your view of a particular system, and eventually it's going to become closed. and this law of conservation of energy will apply. All right? All right, let's look at a couple other definitions, and then we'll do a concept test. Can I go down from here? Okay. Power, we're going to look at. And you'll probably see some simple calculations on the next exam or even on the next reading quiz. Power is the rate of using energy. Power, which I'll use a capital P, is equal then to the, if it's a rate, it's going to be energy over time. Whatever type of energy you're dealing with, it's going to be energy over time. You might know what the units for power are. Well, I know if I just look at this, the units for energy are joule, and the units for time are seconds. So what is the unit for energy? The what? What? That's the watt. I do that joke every year. You get it? What is the joke? What is the unit for power? Watt. Right. I thought that was pretty good. Okay, so a joule per second is a watt. You see it on your electrical devices as a capital W, or you might see it motors. They have a wattage. They have a certain power. What else has a wattage? Light bulbs, yeah, all the light bulbs. Any electrical device will have a wattage rating. When we get into electrical energy, we'll use that quite a bit. But we also use it in mechanical systems as well. Let's do a concept test. Let's just do a few questions. If I understand correctly, we've done these, but we stopped when we got up to kinetic energy. That's correct, we have not done this. All right, let's try this. By what factor does the kinetic energy of a car change when its speed is tripled? Remember the expression for kinetic energy? It was 1/2 mv squared. 1/2 mv squared. I'll give it to you now, but you won't have it on the quiz. So, the kinetic energy is 1/2 mv squared. So if I change its speed by a factor of 3, how does the kinetic energy change? Okay, I'll stop at 53, 50, 55, 55. Okay, D here is right. These are good questions, and if you ever take any standardized tests, even if physics isn't on that test, if there's any quantitative things on it, these are good types of questions. Like they'll ask you about a formula, and if you change one of the variables, how does that affect the other variables? Are any of you pre-professional? Fazal? Yeah, Elise? Yeah. What are y'all? Pre what? OT. OT? PA. Huh? Yeah, okay. And this course is okay for that? All right. OT is occupational therapist. Are you quizzing me? Physician's assistant. Physical therapist. I know all this stuff. I've been here for 8 years. I've had a lot of y'all. Huh? What? Thank you, Casey. Let me write your name down. That was very good. Okay. Kinetic energy is 1/2 mv squared. Right? And so if I increase V by a factor of 3, that's 3 squared. So this increases by a factor of 9. Right? And you'll see those on my test as well. 2 stones, one twice the mass of the other, are dropped from a cliff. just before hitting the ground, what is the kinetic energy of the heavy stone compared to the light one? So big stone and a little stone are dropped from the same height. When they reach the bottom, what is the kinetic energy of the heavy stone compared to the light one? This one has M, this one has 2M. I'll stop at 115, 115, 7 more seconds. Let me remind you of something. I'm gonna give it to you again because a lot of you are getting this wrong. Um, no, you're not. No, most of you got. Never mind. I'll just gonna show you and then I'll get it. D is right. It is twice as much. Sorry, I was looking at the wrong thing. The heavy stone. Why does the heavy stone have more energy than the? Right. You're not squaring the mass. You're only squaring the velocity. But remember, we had this early on. If I drop a heavy object on a light object, like this paper and my keys, right? One's heavier than the other, right? This is quite a bit heavier, but they're going to fall at the same rate. They have the same acceleration, and so they'll have the same velocity at the bottom. So you can think of it in that way, that the kinetic energy at the bottom is 1/2 mv squared. And the big stone, I'll call this KB, has a mass that's twice that of the little stone. So it's going to have twice the kinetic energy. But the velocity is going to be the same. Another way you might want to think about it is that the potential energy up here of both of them is going to equal m times g times h. They're both at the same height, and all of this potential energy is converted to kinetic energy at the bottom. So up here, the one with the bigger mass, since they're both at the same height, will have more potential energy. Is that clear? Well, kind of, maybe? Okay. We'll see some more questions. All right. In the previous question, what is the final speed of the heavy stone compared to the light one? I think I said this, actually, so if you're listening. I'll stop at 40. Stop at 40. Very good. Kid's on a skateboard at 2 meters per second. Force acts on the kid. Then her speed is 3 meters per second. What can you say about the work done? Well, think work energy theorem. Remember the work energy theorem? If I do work on an object, changes its energy. Stop at 45. 45. Very good. So this sort of goes back to what we were doing a few days ago. if the force and the displacement are in the same direction, that's positive work. But also you can think of it as if the kinetic energy increases, that's also positive work. Work causes an increase in energy. Or negative work causes a decrease in energy, like the catcher catching the ball. Car starts from rest and accelerates to 30 miles an hour. Later it gets on a highway and accelerates to 60 miles an hour. Which takes more, 0 to 30 or 30 to 60? Think about your change in kinetic energy. I'm going to stop at 35. 35. All right, look. Our change in kinetic energy, that would be our kinetic energy final minus our kinetic energy initial. All right? That's going to be 1/2 m vf squared minus 1/2 m vi squared. Right? And so this is going to be the same as 1/2 m times vf squared minus vi squared. So what I'm asking here, guys, is what's different or what's bigger? Is it 30 squared minus 0 squared? Or is it 60 squared minus 30 squared? Does anybody know which of those is bigger? Let's try it. All right, so I'll try again. Which of those is bigger, 30 squared minus 0 or 60 squared minus 30 squared? Thirty squared is 900, right? 60 squared is what? 3,600. All right, I'm going to stop at 35. Y'all are still pretty split on this, but I'm going to go ahead and make the point. 35. Yeah. The answer is B. Good job, the two of you. Anybody want to admit to getting that one right? That was good. Oh, man. Listen, if you just look at the numbers, right? 30 squared minus 0 squared, that's equal to 900. This is equal to 3,600 minus 900, which is 2,500. So there's a much greater energy required to go these faster speeds. Even though you're changing by the same amount, it requires a much greater energy to go from 30 to 60 than from 0 to 30. In fact, if you were to plot the energy, so if you plot the kinetic energy versus the speed like this, it looks like this. It's a parabola, right? And it goes up, and it starts going up really fast when you get to those high speeds. So when you're out in your car, and you're going at a high speed at, I don't know how y'all drive, but 55 or whatever, you have to know that to go from 55 to 60 requires a much greater amount of energy than to go from 0 to 5. A much greater amount of energy. That's why there's more to it than just this, but that's one of the reasons why you get better gas mileage at lower speeds, at around 45 miles an hour. That's all? No, I don't think so, because you would be shifting gears at the higher speeds, and so your engine might spin at the same rate, but it still requires more energy. Yeah, but I'm not sure. I think so. Yeah, I'm not sure. I think so. Ask it again. Uh-huh. Right. You certainly have to shift a gear from what you're doing at 5, right? Yeah, I mean, you were in first gear at 5 miles an hour, yeah. And so, I'm not sure I'm not sure I either understand or know the answer. Okay? All right. So higher speeds require more energy. And even changes in higher speeds require more energy. Okay, is it possible for the kinetic energy of an object to be negative? A or B? Just to be honorary. Okay, 35, I'll stop. Okay. I don't know that it was stated this explicitly, but the answer is no. You should know that just from looking at the equation, however, because the equation says that the kinetic energy is equal to 1/2 mv squared. The mass can never be negative, and in fact, this that we're using here is not the velocity, it's the speed, which is like the magnitude of the velocity, and it can't be negative either. But even if you did make this negative, that negative would go away. So just the math of it makes it so it can't be positive, can't be negative. But also we would, gosh, did we talk about scalars and vectors? We did, didn't we? Yeah, so kinetic energy then, do you think is a scalar or a vector quantity? It's a scalar quantity. Very good. It's a scalar quantity, meaning that it doesn't have any direction, and so it's only going to be positive. Right? Meaning that the negative would denote some direction. All right. Here I have two paths. They go up a mountain. One path goes straight up the mountain. The other path goes like that up the mountain. How much more potential energy do you gain if you take the longer path? The longer path is twice as long. Stop at 1 minute. 1 minute. 5 seconds. Okay. Um, both of you start at h equals 0, right? You both start at h equals 0, and then you both go up a height h, we'll call it. We'll call this 0, and we'll call this h. Remember, potential energy, which we called u, is equal to m times g times h, right? Let's try it again. How do your potential energies differ, whether you take the long path or the circuitous path? All right, looking a lot better. I'll stop at 38, or we'll go to 40. Not that much better, actually. We'll stop at 40. Okay, A is the right answer. You gain the same amount of potential energy. You were probably confused about this, right? Because it's going to take which path will require the most energy overall to go up. Which one, the longer one or the shorter one? The longer one, right. It's a longer path, and as you go along that path, you face a lot of frictional forces along the way that are going to impede you. But here we're not asking that. We're just asking how does the potential energy change? And the potential energy is going to be the same for both. Oh, let's do the other one too. Yeah, they'll go. There's a place on the website where you can find them. Oh, really? I'll put them up. Okay, so a mass attached to a vertical spring causes the spring to stretch and the mass to move downwards. What can you say about the spring's potential energy and the gravitational potential energy of the mass? We didn't talk about this yet. We'll get to it in a later chapter. But if I have a spring, I think we did talk about it. Remember the rubber band? If I stretch a rubber band, it has potential energy. If I stretch a spring out, it also has potential energy, elastic potential energy. And so here I have a mass that's on a spring. It actually is vertical, not horizontal. And it stretches out in this direction. Put the mass on the spring and it stretches down. What happens to the potential energy of the spring? That's what we call U. And the gravitational potential energy. All right. Stuff about 122. All right, B is right. Okay, as you stretch out the spring, Elise, it's going to be okay. As you stretch out the spring, uh, the potential energy of the spring increases, right? And but the gravitational potential energy of the mass decreases because it's lower. Its H value is less. All right, let me write this name down. Okay. Okay, here we have 3 ramps. We're assuming them all to be frictionless. Okay, there's no friction acting here. Which ball has the greater speed at the bottom of its ramp? Let 1 be A, 2 be B, 3 be C. And then R is at D, the same speed for all balls. One is A, 2 is B, 3 is C. I don't think so. Yeah, there are 4 options. D is same for all balls. I mean, it's not meant to be a trick question, but most of you have it wrong right now. Like 80% of you have it incorrect. I don't know what y'all put, but most of you are wrong. Do y'all like it when I tell you that most of you are wrong? Or does that just frustrate you? Right. Okay, more of you are becoming right. All right, I'm going to stop at 135. Which has the greater speed at the bottom of the ramp? 135. Yeah, you see? Who's the most confident? It is D. All right. There should be some way on tests to list not only your answer, but then your confidence in the answer. And then somehow account for confidence in grading. Don't you think? All right. So, look, guys, they all have the same potential energy up here. They all have the same potential energy. And so they're all going to have the same kinetic energy at the bottom. And so they're all going to have the same velocity at the bottom. Now, the reason you put A, I suspect, is because initially ball 1 is going to roll faster, right? And it's also going to take less time to get to the bottom than ball 3. Ball 3 rolls more slowly, but it requires more time. And in that time, it gets to the same speed as ball 1, or ball A. Now let me ask you the same question. What if there were friction involved? So what if on each of these tracks there was a frictional force acting on the ball, pushing on the ball, frictional force? So imagine instead of a ball, imagine a block sliding, if that helps you. A block sliding down the inclined plane. Which one is going to be going faster, or would they all be the same? Hmm? Right. Except for the difference that, the paths are different. But yeah, the frictional force is the same for all three. Yes, answer, please. Y'all hang in there. Just about 10 more minutes. I'm going to hand back your quizzes, okay? All right, I'll stop at 105. 105. All right, A is correct. When we think about the frictional force, no, kooky today. So the frictional force does what kind of work? Does the frictional work do positive work or negative work? It does negative work on the block as it slides down, and so it takes energy away from the block, and the amount of energy that it takes away from the block is dependent upon the length of the path. So here the path is a lot shorter, and so the friction takes away less energy. It does less negative work than it does over here. Over here it does a lot of negative work, and it takes away a lot of the block's energy. All right? These are good ideas that you need to understand, this whole idea of work and energy being related, or even the same. We might think about them being the same, and how we can think of work as being positive or negative and taken away from energy. Okay, we just have a few more. We'll wrap this up and I'll hand back your quizzes. Who did more work, Mike or Joe? I'll stop at about 1 minute. 1 minute. 1 minute. Okay, who did more work? No, they did the same work. I'm sorry, I was distracted by the comedy going on back there. I'm not sure what's going on, but I don't think these problems are that funny. Are they? Look, guys, the work is just force times distance, and so Mike does 10 newtons times 3 meters. That's 30 joules, and then Joe does the same. They do them in different times, and so their powers are going to be different, but they do the same amount of work. Let's try this one. This one's a little bit similar. Here I'm asking about the power. Mike does 5 joules of work in 10 seconds. Joe does less work, 3 joules, but he does it in 5 seconds. So who produces the greater power? All right, I'm going to stop at 55, 55. And Joe did produce more power, right? Yeah, very good. And you just take the power over the time. Even though Joe does less work, hey guys, even though Joe does less work, it's 3 over 5. That's 0.6 what? Watts. It's 0.6 watts. Yeah. Hey folks. Folks. I appreciate that you're having a good time. But huh? Yeah, so that Mike is doing 5 joules of work in 10 seconds. And so that power is 5 over 10, which is a half a watt. And Joe, on the other hand, is 3 over 5, and so that's 0.6 watts. 3 over 5 is 6 over 10, or 0.6. So Mike does 0.6 watts, or 0.5 watts. Joe does 0.6 watts of power. Less power, but in less time. So less work, but in less time. All right, just a couple more. We'll wrap it up. Engine 1 produces twice the power of engine 2. So watts, for example, is similar to horsepower, but just a different system. Engine 1 produces twice the power of engine 2. Can we conclude that engine 1 does twice as much work as engine 2? Yes or no? And actually, after this, I'll have one more little topic. It'll just take a couple minutes, because then we'll move on into temperature next time. I'm going to stop at 50 seconds. Sorry for lying to you, but so B is right. Just because you have more power doesn't mean you necessarily do more work, because it depends upon the amount of time that you're running. Now let's try this. You want to do some dimensional analysis. Your electric company, you pay by the kilowatt hour, kilowatts times hours. What? No, you haven't seen any of this. You're paying for energy, not for power, is the point here. A kilowatt hour, even though kilowatt is in units of power, it's joules per unit time, and then you multiply that by a unit of time, which is hour, and so your times cancel, and so you're paying for energy, not power. All right, so A is the right answer. I'll go and click in A. The idea here, the power company, they don't care how quickly you consume energy. You could do it all on the first day, in which case your power consumption will be really high. But they don't really care about that. They just care about the total amount of energy that you consume. Stop at 1 minute. A is the right answer. They talk about this a little bit in your book as well. All right. I will put these up on the internet, on the website. And am I missing one that I haven't put up? I might be. I'll put it up as well. These are good ways to prepare for the exam. Let me just cover one quick topic before we hand back your quizzes. Again, I'm sorry for lying to you, but that's just sort of what I do sometimes. And that is efficiency. This is closely related to power. When you hear talk about motors, you'll hear talk of their efficiencies. Efficiency is just the work output over the energy input. And that's times 100%. So for example, if I put in, if my motor or whatever consumes 100 joules of energy, so if my energy input is 100 joules of energy, but it only produces 50 joules of useful energy, what is my efficiency? Right, it's a half or 50%, right? And so we use this to describe our efficiency of a motor. You can never have an efficiency of a motor that's greater than 100%, right? Because of this whole idea of the conservation of energy, that you can't just produce energy out of nothing. All right, let me just do a quick little sample problem, and then I'll hand back your quizzes. An engine has an efficiency of 20%. It produces an output work of 20 joules. How much energy was lost? And I'll just work it here for you. How much energy was lost? So your book does a similar problem. Um, so my efficiency is 20%, and that's equal to the work output over the energy input times 100. And so let's see, our output work was 20 joules. 20 joules. So I just solve here for energy. So I can do that. I can divide by 100 and divide by 20 on both sides. And that cancels that out, and it cancels that out, cancels that out. And I get that 1 over 100 equals 1 over my energy. So my energy is equal to 100 joules. So how much energy was lost? No, that was fast. 80 joules was lost. All right. We'll come back. We'll revisit that. That's really the only type of problem that you would see regarding efficiency, or you could be solving for any of the other ones. But we'll revisit that on Tuesday just briefly. And then also it's in your book as well. All right. We're about to move into the physics of the body soon. Don't forget that your quiz is on Tuesday. That'll be at the end of class, the last 20 or so minutes of class. I'm going to hand back your quizzes right now.